Now let's take a look at permutation. A permutation of n different elements is an ordering of the elements such that one element is first, one is second, one is third, and so on. So in this case, permutation in permutations, order matters. So find the number of permutations. How many permutations of the letters A, B, C, D, E, and F are possible? So let's just go with the first position. So we have 1, 2, 3, 4, 5, 6 letters. So in the first position, I have 1, 2, 3, 4, I have 6 choices, right? There are 6 letters. Then once I choose that one, I can't choose it again. So then 5 choices, and then 4 choices, 3, 2, 1. And so really, we're looking at that many possibilities, and you multiply it all together, and so there are 720 permutations. Now, when you see this ordered like this, and you're multiplying them together, I hope it reminds you of something, that we can look at it as 6 factorial, right? That's the same thing as this 6 times 5 times 4 times 3 times 2 times 1. So there are 720 permutations. Try out this next example here. How many permutations of the letter W, X, Y, and Z are possible? So you have 4 letters. So 4, 3, 2, 1. So therefore it's 4 factorial. And then there are 24 permutations. So the number of permutations of n elements is n times n minus 1, 4 times 3 times 2 times 1, which is n factorial, which is what I stated earlier. So in other words, there are n factorial different ways of ordering n elements. Now it is useful on occasion to order a subset of collection of elements rather than the entire collection. For example, you may want to order r elements out of a collection of the n elements. Such an ordering is called a permutation of n elements taken r at a time. So we're going to look at that example next. So here's an example. Counting horse race finishes. So 8 horses are running in a race. And how many different ways can these horses come in first, second, and third? Assume that there are no ties. So if there are 8 horses, so there's first, second, and third, right? So one is going to be first, one is going to be second, one is going to be third. So in the first place, there are 8 possibilities here, and then the second place, there are then 7 possibilities, right? Because one already won, so you can't that can't win again. So 7, and then times 6. So now we're looking at 8 times 7 times 6 different ways, which ends up being 336 ways. So try this example here. A coin club has 5 members, and how many different ways can there be a president and a vice president? So the president and the vice president, so there are 5 choices, and then once that person's chosen, there are 4 choices. So therefore, there are 20 ways that there could be a president and vice president. So here's a formula that we could use. Permutations of n elements taken r at a time. The number of permutations of n elements taken r at a time is npr, which is n factorial over n minus r factorial, and then you see this information here, n times n minus 1 times n minus 2, and so forth. So what we can do is let's go ahead and do this horse race one. So what we're saying is that there are 8 horses, and then we need 3 out of them. So then what we're going to do is plug it in, 8 factorial over 8 minus 3 factorial. So this is 8 factorial over 5 factorial. So 8 times 7 times 6 times 5 factorial over 5 factorial. And so we get the same exact thing, right? So I know in this case it's probably faster to do 8 times 7 times 6, but there are going to be occasions where we're not going to want to do that. Distinguishable permutations. Consider a set of n objects that has n1 of one of a kind object, n2 of a second kind, n3 of a third kind, and so forth. So the number of distinguishable permutations of n objects is n factorial over n1 factorial times n2 factorial times n3 factorial all the way times n sub k factorial. So let's try that. What does that mean? So let's look at this example here. And how many distinguishable ways can the letters in banana be written? So notice We have some letters that are repeated. So B, there is 1. A, there's 1, 2, 3. So A, there's 3 different ones. And then N, there are 2 different letters, right? So we have a total of 3, 4, 5, 6 letters. So N is 6, and then let's write this out. We have 6 factorial, we're using this here. Then the first one, we have 1 factorial. For A, we have 3 factorial, and we're multiplying those all together, and then times 2 factorial. So we have 6 factorial, or 6 times 5 times 4 times 3 factorial. Let's do that. And then 1 factorial is just 1, times 3 factorial times 2 times 1. So 3 factorial cancels. We get 2 goes into 4 2 times. So 6 times 5 is 30 times 2, which is 60 different ways. And then if you're interested, you can look at the book because it lists them all out. Now, try this example. How many distinguishable ways can the letters in mitosis be written? So if you tried this out, there are 7 total letters. M, there's 1, I, there's 2, T, there's 1, O, there's 1, and S, there's 2. So you should list it out like this, and then multiply all the way through. You'll find there's 1,260 ways that mitosis can be rewritten.